watch as the frog leaps from the jetty and into the water. When something is in the process of changing position, it is moving. We say it is in motion. Motion is movement in any direction. So what are some ways we can describe motion? An airplane is in motion as it speeds down the runway. It moves in a straight line and then up into the sky. A person on a swing usually moves in a back and forth motion. On a seesaw, the people move up and down. On a carousel, they move round and round. What are some other ways you can describe motion?
Hello, and thank you for watching this video about reference points. A reference point is a place or object used for comparison to determine if something is in motion. Basically, you're finding something to look at in order to decide if you or something else that you see is moving or not. You're using that object as a reference. Let's use an example. Let's say you are in a car about to leave home and go to the store. You aren't moving yet, but how do you know? That may sound like a silly question, but you know because you are using something or many things around you as reference points, such as a tree, or the driveway, or your house. These are all examples of reference points that you can use to determine whether or not you and the car are moving. When you and the car are sitting still, you can look at the tree and the house and the driveway and see that your distance to all of them isn't changing. However, if you start to drive away, you can look at the tree and the house and the road and see that they all appear to be getting further away from you. Now you know that the tree and the house and the driveway are all stuck to Earth's surface. They aren't moving or going anywhere, so it must be you who is moving away from them. You can look at these objects sitting still on Earth's surface and know that you are moving. But we don't have to use only objects that are stuck on Earth's surface as reference points. We could use moving objects too. Let's say you're driving next to another car, and that car is going the same speed as you. You're driving along looking at the other car, and since you're both moving at the exact same speed next to each other, it doesn't look like either of you are moving. If you use only the other car as a reference point and ignore everything else outside that you see, you are both not moving. Relative to the red car, you aren't moving. You could look at the driver inside of your car too, and relative to them, you aren't moving either. Now, I know this sounds really silly because both you and the other car definitely are moving because you're in a moving vehicle. But relative to or compared to the other objects around you moving at the same speed, it doesn't look like you guys are moving. That's why when we're discussing movement, it's important to choose a reference point that makes sense for that situation. In most cases, when discussing moving objects or figuring out if something is moving or not, it makes the most sense to use objects that are stuck to Earth's surface or are sitting still, like trees and buildings. You know that if a tree or building appears to be moving toward or away from you, you know that it's you that's moving.
Force and motion. Imagine you're playing in a playground. Think of all the things around you that can move. The seesaw goes up and down. The swings go back and forth. The merry-go-round goes around in a circle. There are so many ways in which things move. Everything we just described is a type of motion. Motion is movement from one place to another. When the seesaw is still and you and a friend sit on it, it begins to have motion. One seat goes up while the other goes down. They change their positions. Position is the place where you are. If you change your position, you are moving. There are different types of motion. If you swing on the swings, that's a back and forth motion. It's also an up and down motion. If you ride on a merry-go-round, you'll be going round and round in a circle. If you run forward with a back and forth motion to dodge a friend while playing tag, that's a zigzag motion. Or you can run in a straight motion to the base. There are also different speeds of motion. Speed is how fast you move. What speed do you go at when you're on the swings? It can be fast and exciting, or slow and relaxing. On a merry-go-round, you can start off slow and go faster and faster. You may run fast when you pass your friend playing tag and slow down when you get to base. Many things are in motion around us, but some things are standing still. How do we get them in motion? What makes something move? Think about a toy car or truck. Pretend it's sitting on the floor in front of you. How could you get it to move? You might use your hand or foot to push it away or pull it toward you. You might hit it with another object, for example, a ball. You could even blow on it. There are many ways to get things to move. The push or pull that we use to make things move is called a force. A force is needed to make anything move. Let's look at things a person pushes and pulls in one morning. This man pushes an alarm clock to make it stop ringing when he wakes up. He pulls the blankets off himself and uses his legs to push his body up. He pulls open a cabinet to get out his breakfast. He pulls out a bowl and a spoon. He pulls the chair back to sit down and pulls it back in under the table. His teeth push and pull the food. When he's done eating, he pulls up all the food items on the table and pushes them back in the cabinet or fridge. He pushes a washcloth across the dishes to clean them. That's a lot of pushes and pulls. Now, let's use another example of motion. Riding a bike. You use force to get a bike to move. How? By pushing and pulling the pedals. Once the bike is moving, what else can you do? You can go faster by using more force, pushing and pulling harder. You can slow down by using less force, not pushing and pulling as hard. You can change which way you're going by using force, by pulling the handlebar, which pulls the wheels in another direction. What can you do to stop? Well, you can do two things. You can use force to stop by putting on the brakes. Or you can just stop pedaling, and you will stop moving after a while. That's because there's another force acting on your bike's wheels. It's called friction. It means the wheels are rubbing against the road, and that rubbing will eventually slow them down to a stop. But if there were no friction and no other force stopping it, your bike would just keep rolling on forever. Now let's summarize what we have learned.
In this video, we're going to talk about the difference between distance and displacement. If this car moved from point A to point B, we could say it traveled a total distance of 100 meters. Distance is a measurement of the length between 2 points. Now let's go back to this example and add another road sign here. Let's bring this one in so we have a direction. Now if the car again traveled from point A to point B, we could say that it traveled a distance of 100 meters, but we can add in another part of this measurement. We could say it traveled 100 meters to the east. And this is actually a displacement rather than a distance. The difference is that we're including a direction this time around. Now the definition for displacement is the overall change in position. So we're looking at a starting position comparing it to a finishing position. And then the other big difference here is that displacement is going to include a direction. Now, displacement includes a direction, and so we call this measurement a vector. And so measurements that include directions are called vectors. Distance doesn't include a direction, and so it's called a scalar. Let's add another road sign here in our example. So if we add this extra midpoint here road sign, we'll bring our car back to the point A, and if the car travels from point A to point B and then just backs up here to the center here, let's see how far it traveled. Now it's traveled a distance there from point A to point B of 100 meters, and then it traveled an additional 50 meters for a total distance of 150 meters. Now if we look at its displacement, however, we're comparing its starting position, which was right here, to its finishing position, which is right here. And so its total displacement would be 50 meters to the east. In other words, it's 50 meters east of where it started, which was right here. Let's look at another example here. If you've ever run track and field, you may have had the chance to run the 400-meter race. The 400-meter race is one lap around the track, and for a total distance of 400 meters. Now, what would the displacement be? Well, if we compare your starting position right here to your ending position right here, we would say that your total displacement was 0 meters. And it's almost like if you were running the race and all the fans just shut their eyes as soon as the gun went off and then opened them again when it was all over, and it looks like you're in the exact same location. Your displacement is 0.
In today's video, we're going to look at the terms speed and velocity, and see how we can calculate each of them. As we saw in a previous video, quantities can be of two types: scalar or vector. Scalar quantities only have a magnitude, which is the size or extent of something, whereas vector quantities have both a magnitude and a direction. So speed would be considered a scalar quantity because it only conveys magnitude. This might be a person running at 4 meters per second, or a plane flying at 250 meters per second. Velocity, on the other hand, is a vector because it also has direction. like a person cycling 6 meters per second east, or a train travelling backwards at 55 meters per second. It's really common in the exams to get speed and velocity confused. So just make sure you're completely sure about which one's which, and try not to get them mixed up. Another pair of quantities you need to know are distance and displacement. Distance is a scalar, as it only gives magnitude, like 10 meters or 40 miles. Displacement, though, is a vector, as it has direction as well. For example, a person running 40 meters east, or a ball that falls 2 meters downwards. To help us understand this difference, let's imagine that we have a train travelling across a bridge. The bridge is 550 meters long, and it takes the train 10 seconds to cross it. To calculate the speed of the train, we need to take the distance it travelled and divide it by the time that it took. So 550 meters over 10 seconds, which gives us the scalar quantity of 55 meters per second. If we took this same equation, but replaced the scalar quantity of distance travelled with the vector quantity of displacement, we'd then be able to get the vector quantity of velocity. If we knew the direction that the train was travelling in, for example east, then instead of writing the distance, we could write the displacement, which would be 550 meters east. The time would still be 10 seconds, and the velocity would still have a value of 55. But the units of the velocity would be meters per second east, rather than just meters per second, like we've got for speed. Now, the symbol formulas for these two equations can be kind of confusing, because they use the letter S to represent different things. For velocity, the S refers to the displacement, but in the speed equation, the S stands for speed, and the D is distance. In both cases, though, the T stands for time. In reality, people often use the velocity equation regardless of whether they've actually got a direction or not. The benefit of using velocity is that you can have a negative velocity to represent going backwards. Now, often objects don't actually move at a constant speed, but instead vary along their journey. We can still use this equation, but we need to divide the total distance or displacement by the total time that the journey took. And the value that we calculate will then be the average speed or average velocity. To give you an idea of real-life speeds in meters per second, people walk at about 1.5 meters per second, run at around 3 meters per second, and cycle about 6 meters per second. All of these numbers do of course vary a lot though, depending on the age and health of the individual, and how much effort they're putting in at the time. Then for vehicles, a car on the main road might travel around 25 meters per second, while a fast train could travel 55 meters per second, and planes can exceed 250 meters per second. It's not only the speed of objects that varies though. As we'll see in a later video, sound waves travel at 330 meters per second when they're in air, which is a figure that you need to remember. But when they're traveling through different mediums, like water, their speed changes. A more relatable example is the wind, which is just the natural movement of air. This can vary from almost 0 meters per second on a still day to faster than a speeding train on a windy day, and can be affected by things like temperature, atmospheric pressure, and these structures it's traveling past, like buildings or mountains.